Assalamu alaikum. So, welcome to the 19th lecture of the Condensed Matter Physics course. Now, we're going to shift gears a little bit today. In the previous 5 lectures, we've seen free electrons, we've seen nearly free electrons, and we've discussed how a weak periodic potential modifies the free electrons and converts them into nearly free electrons, how the dispersion relationship changes, and how band gaps appear, and how the very concept of bands comes to the fore. We've also introduced the block theorem in the process, and we've seen that block functions become eigenfunctions of the periodic potential problem. These block functions are plane waves, but modified slightly by the periodic potential. So they are not really the plane waves, but almost the plane waves. They are nearly free plane waves. So today we're going to look at the other extreme. So far, we've seen a weak periodic potential. So we started off with the free electron wave and imposed a weakly perturbing periodic potential and saw how the free particle wave was modified. And the energies corresponding to the free particles, they were modified, especially near the zone boundaries. Today, we're going to start looking at this from the exact opposite angle. This means that the periodic potential is rather strong and it tries to hold the electrons close to the atoms. In the weakly periodic potential case, the electrons were started off by assuming that they were largely free and they were roaming about inside the metal. And the ionic core, the template of ionic cores, only slightly perturbed those wave functions. However, now we have the converse situation. We start off with atomic orbitals in which the electrons are tightly bound to the nucleus. So let's get started. Our lecture number 19 deals with strong periodic potentials. And more precisely, we are going to talk about the tight binding model today. So in order to invoke the tight binding model, let me start off by a discussion of the hydrogen molecule, positively charged dihydride molecule, which comprises of 2 protons, which are the nuclei, and an electron, a single electron. So this is just a cartooning picture of the scenario. The electron has a particular position vector small r, and the 2 nuclei, which I can label as 1 and 2, they have position vectors capital R1 and capital R2, and I assume that the nuclei are fixed in position. And I invoke an approximation which is called the Oppenheimer approximation, in which the electron moves in the field produced by 2 static protons, 2 static nuclei. Now, the single electron inside this molecular system can be described by a Hamiltonian, and the Hamiltonian will be given by the kinetic energy of the electron and the interaction of the electron with the first nucleus and the interaction of the electron with the second nucleus. And we all know that this interaction is of the electrostatic or the Coulombic kind. So V1 would be given by minus E square over 4 pi epsilon naught R minus capital R1 magnitude. And likewise, V2 will be given by minus E square 4 pi epsilon naught R minus R2. So we just had a single nucleus, then we would just map this problem to the problem of a hydrogen atom. But now we have 2 hydrogen nuclei and a single electron. So problem is slightly more complicated. Now, in order to start this problem, we also assume that if these 2 atoms were isolated, they were really, really far apart, and we only affix a single orbital to one atom. So atom 1 has one orbital and the atom 2 has another orbital. And the orbital is just an eigenstate of the Hamiltonian for the single atom. So these are two separated, isolated atoms. And we just assume that we're dealing with the ground state. So just one orbital is enough, and we have an electron here. And we know that we can define an orbital called ket1, which is signifying that this orbital belongs to the atom 1, and we know that this will be an eigenstate of the Hamiltonian for atom 1, which will be k plus v1, just v1, no consideration of v2 whatsoever. And the energy, let's call this energy E naught. So E naught is the eigenstate or is the eigen energy of the Hamiltonian corresponding to the first atom. The second atom is totally identical. So if we were to define an atomic orbital ket2 that belonged to the second atom, and we're using ket2 because we would like to distinguish it from the first atom, then this is going to be an eigenfunction of k plus v2 with the same energy because the two atoms are identical. So this is our starting point for the discussion. Now what we would like to do is we would like to bring these atoms closer together. So they are coming closer together, and when they come close together, at some point there is the potential for making a molecular bond or making a covalent or an ionic bond. The electron is now all of a sudden seeing two nuclei. So the Hamiltonian is going to change. And we assume that the Hamiltonian is now of this form, H equals K plus V1 plus V2. So now the eigenfunctions will also change, and the eigen energies are also going to change. So suppose we have two, just to give you another example, suppose we have these two circuits. Those who are fond of dealing with circuits would really like this example. Two LC circuits or two tank circuits. Each circuit has a characteristic characteristic frequency. Depends upon the inductance and the capacitance. Now, when these circuits, these oscillating circuits, these tank circuits are brought close to one another, new energies appear. One is omega 1 plus omega 2, and the other is omega 1 minus omega 2. So now we are bringing atoms closer together. So the eigen energies are going to change, and so will the eigenstates. So in order to find out those eigen energies, we have to resort to the time-independent Schrodinger equation again. And we know that the time-independent Schrodinger equation is given in this form. Now, how do we find out the eigen energies? First of all, we have to propose a particular possible trial solution. Whatever the case may be, we always know that the Hilbert dimensionality of this electron is still 2, which means that we need two basis vectors. Those basis vectors can be the atomic orbitals themselves. So we create superpositions of these atomic orbitals, and we propose that this is our trial solution. And solving the Schrodinger equation means finding these coefficients C1 and C2. So now let's put in this trial solution into the here. So this is our left hand side. Now H is K plus V1, and this acts on our trial solution. This is the left hand side of the time independent Schrodinger equation. So what we could do is write this in this form: V2 ket1 plus K plus V2 acting on ket2 plus V1 acting on ket1. All right. Now comes the really interesting part. Let's find the projection of the left hand side on ket1. If we were to do that, now another thing that I forgot to mention earlier is that I assume that my atomic orbitals, they are orthogonal, which means that if an electron is in ket1, it can't be in ket2. So there is very little overlap between the two atomic orbitals. And of course, this is an approximation, because if there were no overlap, there will be no possibility of cross terms. But let's assume for the time being that our atomic orbitals are orthogonal to one another. So if you were to take the projection of the left hand side on ket1, which means we form the inner product of the left hand side with bra1, what we would get is now when this Hamiltonian acts on one of its eigenstates, we simply get the energy E naught. And the overlap of ket1 with itself is 1. And this term would give me C1, bra1, V2, ket1. Likewise, this term is going to give me epsilon. So I would write C2 epsilon naught. However, the overlap with ket1 is 0. So I'll get a 0 here plus, by the way, there's a C2 here. C2 bra1 ket V1 ket1. So the projection of the left hand side is C1 naught plus C1 bra1 V2 ket1 plus C2 bra1 V1 ket1. Now let's look at the right hand side. The right hand side of the Schrodinger equation is epsilon psi, which is epsilon ket1 plus C2 ket2. Now let's take the projection on ket1. This will leave us with epsilon naught C1. Now I can equate the two projected scalars, and when I do that, by the way, the left hand side has a C1 epsilon. So by the way, the right hand side doesn't have an epsilon naught, so sorry about that. This is simply epsilon, the energy, the total energy that I seek to find. All right, now if I am going to equate the left hand side with the right hand side, the projections on ket1, I am left with C1 epsilon naught plus C1 bra1 V2 ket1 plus C2 bra1 V1 ket1. This equals epsilon C1. So let me just do a bit of reshuffling. Epsilon naught plus bra1 V2 ket1 C1 bra1 V1 ket1 C2 equals epsilon C1. Let's call this equation number 1. Let me put it in a box. Now if I were to take the left hand side and find its projection onto ket2 instead. So let me see what the left hand side is again. Here it is. So let me try to reduce the size a little bit so that I can see everything in one go. So if I find a projection on ket2, I can perform this calculation, and let me try to write down the result here. Let me look up my notebook. I can simply write down the result, which is very simple, and it's going to be bra2 V2 ket1 C1 plus epsilon naught plus bra2 V1 ket2 C2 is epsilon C2. Now this is my second equation. So this is something for you to do on your own. Now if I look at equation number 1 and equation number 2, I can cast this in matrix form. This fashion. I'm sorry, there is V1. Sorry, here there has to be a catch 2. Catch 2 here. So this has to be catch 2. Sorry about that. So bra1 V1 catch 2, and here I have bra2 1 naught plus bra2 cat 1 V1 catch 2 multiplied with the vector C1 C2 gives me energy C1 C2. Now here the solution psi has been written in matrix form in terms of a column vector with entries which are the complex coefficients C1 and C2. Of course, this is the Hamiltonian here. So now let's look at the terms of the Hamiltonian. Epsilon naught is clear. If I just have a single isolated atom and the electron is seeing the nucleus, the interaction of the electron with its own nucleus and the kinetic energy of the nucleus gives rise to an atomic energy epsilon naught. This term here, first electron can also interact with the second nucleus. It's not a hopping of the electron from one orbital to another. It's just the first electron feels the presence of the second nucleus. It is pulled by the second nucleus. Likewise, this term here is the second electron feeling the pull of the first nucleus. So these are like these terms which are highlighted in purple. They are like cross terms. And they simply shift the energy. They do not result in the hopping of electrons. I'm going to describe the hopping in a minute, but they simply shift the energy of the electron. These terms, on the other hand, deserve our attention. And we can define a scalar T in the following fashion. We can define this term to be equal to minus of bra1 V1 ket 2. Now what does this mean? This means that an electron in the second orbital can be pulled into the first orbital. So it represents a hopping between the second orbital and the first orbital. All right. And this hopping can be achieved either by V1 or by V2 because of the symmetry of the molecule. So this is our definition for T. So this term I can replace by minus T. And if you observe that the term on the bottom left is simply the complex conjugate of this term, so I can replace this with minus T star. Okay. So this is how I define my T. T is a matrix element for any potential which connects one orbital, the electron in one orbital to the same electron in another orbital. All right. So it represents some kind of transfer. That's where the word letter T comes from. Some kind of transfer or hopping between the two orbitals. And we'll see in a minute why this is true. So the Hamiltonian overall can be written by as epsilon naught, which is the bare atomic energy plus some V cross, which is just a shift in the energy. The same terms appear on the upper left and the upper right, and a minus T here and a minus T star here. This is my Hamiltonian. And we can now easily find out the Eigen energies of this Hamiltonian. We simply need to diagonalize the Hamiltonian. And if we were to do that, you can simply diagonalize the Hamiltonian, which means really that you need to find out this characteristic equation and solve for the energy epsilon. And the energy turns out to be E naught plus V cross plus minus the magnitude of T. T, by the way, can be a complex number. So lo and behold, what does this mean? First of all, if you look at the Hamiltonian, the off diagonal terms, suppose they are zero, each T is zero. What would this mean? This would mean that you would have a Hamiltonian epsilon naught plus V cross 0, 0, epsilon naught plus V cross. So this Hamiltonian has two eigenstates. It has ket1 and ket2 as the eigenstates. So if a system that starts off in the state ket1 will remain there because ket1 is a stationary state of the Hamiltonian. Likewise, a system that starts off in ket2 will remain there. The system is in a stationary state of the Hamiltonian. So only when T is non-zero is there a probability that a system that starts off in ket1 can go into ket2. And the cyclic evolution between ket1 and ket2 is going to take place. This is called Rabi flopping. So at any one time, B is going to toggle between ket1 and ket2 with some factor which is going to be proportional to the magnitude of T. T determines the strength at which this mixing between ket1 and ket2 occurs. That's why T is called a hopping term. And this hopping term, of course, it's going to be larger if the atoms are closer together. So if you bring the atoms closer and closer together, this T goes up. And if I were to plot, so let me rewrite the energies. Epsilon is E naught plus V cross plus minus square root of T. If I have the distance between the two nuclei here. So I go from left to right, the distance goes up. And if I go from right to left, T goes up, which means that the hopping term goes up. Now, if the hopping term goes up, the degenerate energy levels, ket alpha and ket beta, which are the eigenstates when these atoms are far apart, the eigenstates are now going to evolve into superpositions, which are the eigenfunctions of the Hamiltonian that I've written. And the energies, one of the energies is going to go up, and the other energy is going to go down. And this is how the evolution with distance is going to take place. So one of these energies is epsilon naught plus V cross plus the magnitude of T. The other is epsilon naught plus V cross minus T. So these energies are now going to split up. And depending upon how close the atoms are, and thus depending upon how large the magnitude of T is going to be, the two energy levels are going to split up. And of course, the wave functions are going to be different. So if you look at the Hamiltonian again, the presence of these off diagonal terms are going to create superpositions as the as the eigenfunction. And those superpositions will be given by 1 plus minus some phase factor ket2, and it can also normalize. So depending upon whether T is imaginary or real, phi can be 0 or 90 degrees. So if T is real, by the way, then we have a sigma x, so phi is going to be equal to 0. So you'll get ket1 plus ket2 as one eigenstate and ket1 minus ket2 as the other eigenstate. So this is the evolution of the eigenstructure of this problem for a single molecule. By the way, these two atomic orbitals separated out, when they merge, they form two new orbitals with different energies. These orbitals are called molecular orbitals. And this one, which is lower in energy, is called the bonding molecular orbital. And the one that is higher in energy is called the anti-bonding molecular orbital. By the way, there's a tacit assumption in all of this, and the assumption is that the two orbitals, they are orthogonal to one another, which means ket1 and ket2, the overlap is 0, and so on. So this really means that the two nuclei are not interacting with one another. But that cannot be the case. If you bring these two nuclei close together, the Born or Oppenheimer approximation also breaks down. So the nuclei are then also going to interact with one another. That is, they're going to repel one another. So if you try to, so what this dispersion relationship is telling us that the lowest energy states would be when this distance r, sorry, or let me write r1 minus r2, excuse me, excuse me. So just give me a second, please. So I think I need to change the batteries here, but just give me a second. All right, so let's continue. So far we've assumed that the atoms, the nuclei don't interact with one another, but really the nuclei do interact with one another. And so this problem is slightly modified. If we were to break down this assumption, ideally what this graph in front of you is telling you is that if this is my distance between the two nuclei, which is r1 minus r2, and magnitude of it, the lowest energy state is when this distance is 0, which means that the two nuclei overlap. Of course, that's not going to happen, because if the nuclei come in close proximity with one another, they try to make a head-on collision, the repulsive force between the two nuclei goes up. And so this curve really shifts up. Okay, this curve really goes up sharply. And therefore, there is a minimum R called R naught, an R which results in minimum energy. This is generally called the bond length. And the potential energy, the dispersion relationship is asymmetric about this equilibrium point R naught, which leads to thermal expansion and so on. But nevertheless, this is the tight binding model for a hydrogen plus molecule. Why is it called tight binding? Because the orbitals are tightly bound to the nucleus per se, but when the two nuclei come close together, there is some finite probability that an electron from one orbital can hop on to another orbital. So the majestic, the glorious, the default position is that atomic orbitals exist, and those atomic orbitals remain tied to certain nuclei. But if you bring these two nuclei close together and start making a molecule, then there is some likelihood that the electron can be transferred from one orbital to another orbital. The Eigen energies are split up, and the Eigen functions, they are no longer the atomic orbitals, rather they are of the form C0 ket1, sorry, C1 ket1 plus C2 ket2, a linear combination of atomic orbitals. So this is a tight binding model applied to a hydrogen plus nucleus, a dihydride cation. Now let's extend this concept to a chain, to the tight binding chain. Now this is a really important concept in all of condensed matter physics, because this leads to the physics of two-dimensional semiconductors, the two-dimensional materials, including graphene and all of its cousins, stannine, black phosphorus, tinine, and so on. So it's very important that we do understand the tight binding model to a fair degree of perfection. So let's start off with a one-dimensional model in which we have a chain of atoms, periodic structure. The atoms are spaced A units apart. Sorry, I just need to, excuse me, let me just, all right, somehow the screen has stopped working again, but give me a second, please. All right, so now let's take this example one step forward and talk instead of a molecule in which we just have two atoms and one orbital per atom. Let's talk about n atoms, capital N atoms arranged in a linear chain, and there's one orbital per atom. All right, so this is our starting premise. So I draw this one-dimensional periodic crystal. Just hope that my technology keeps up with me. So there are n atoms overall. There is one orbital per atom, and these orbitals are labeled cat1, cat2, cat3, cat4, cat small n, all the way up to capital N. So the orbitals are defined such that they belong to a certain atom. So cat3 is an electron orbital belonging to the third nucleus. Cat7 is an electron belonging to the seventh nucleus, and so on. And we also assume, make the assumption that if I have two orbitals, they are mutually orthonormal. All right, so this is another assumption. So now I would like to do the same, take the same approach as I have followed for the molecule. And the approach is that, let me write down the time-independent Schrodinger equation. Here it is. And now instead of having a superposition of two orbitals, my arbitrary quantum state is going to be a superposition of all n atomic orbitals. So I form a general linear combination of all the atomic orbitals, and I put this into my Schrodinger equation. I get H Cn ket n sum over all n's. This gives me epsilon sum over all n's n, right? So this is my time independent Schrodinger equation. Now what I would like to do is I would like to take the overlap on some ket m, any of the capital N atomic orbitals. So I take the overlap, what I get, CnHn epsilon Cn overlap of m with n. So the right hand side is immediately obvious. This will give me epsilon Cm delta mn, where delta mn is the Kronecker delta, which is 1 only if m equals n, and the left hand side could be rewritten in this fashion. All right. So by the way, this is a scalar. It's a matrix element of the overall Hamiltonian, and we can write this down in shorthand notation as the mnth element of the Hamiltonian. So I can write the time independent Schrodinger equation in this form. Okay. By the way, I don't have to write this Dirac delta function here. This Kronecker delta, sorry. All right, so let's look at what this term is going to look like. This is the mnth term of the Hamiltonian, and what is the Hamiltonian? It's the kinetic energy of the electron. And instead of having two potential energy functions, I now have a sum of j potential energy. So this is my H mn. Now, how do I proceed from here onwards? Now, remember that if this is a particular value of n, and this is a particular value of n, and this j is a running variable, it goes from 1, 2, 3, all the way up to capital N. So at some point, it does hit small n. And when it does that, I can write this Hamiltonian in the following fashion: Bn plus sum of all j's, where j does not include n, because I've already included the n factor here. So this term can be written in this fashion. Now, by the way, I can write this, because of linearity, in this form. This will become bra m sum over all j's excluding the n, all right. Now if you look at this term here, get n, the atomic orbital is an eigen state of the kinetic energy plus Vn, where Vn is the potential energy brought out by the nth nucleus, and we're talking about an atomic orbital which is attached to the n nucleus. So this is simply going to be equal to the atomic energy. Let's call this epsilon atom for the time being. This becomes bra m ket n plus, this remains what it earlier was, sum over all Vj of all of these elements. This becomes the Kronecker delta Mn, the energy of a single atom, plus the sum over all these matrix elements. This is my mnth element of the Hamiltonian. Now, this term is clear here. I need to focus on this term. So here I have a sum of matrix elements. M could be the same as n, M could be different from n, and so on. Now there are only three possibilities. I can break up the possible values of m and n into three scenarios. The first scenario is that m is the same as n. The second scenario is that m is n plus 1 or m equals n minus 1, which means that m and n differ by 1 unit, just 1 unit. And the third scenario is otherwise, that is neither of the above. So I can bifurcate my values of m and n into these three scenarios. And now what I assume is that this is a sum of potential. This term, if I were to expand this term, this would look like this. V1 plus V2 plus Vn minus 1 plus Vn plus 1 all the way up to V capital N. And I have to exclude the nth term because the nth term has already been taken care of here. Now, this is a sum of potential energies. It's the sum of the potential energies imposed by all the nuclei but the nth nucleus. All right. Now, if m equals n, so which means that this index is the same as this index, then I'm really saying that the electron, I'm finding out the expectation value of all of these potential energies, excluding the nth, excluding the nth orbital. I'm finding the expectation value in the nth orbital of all the potential energies besides the nth, which now this is slightly complicated. Now this means that an electron is in the nth orbital. We are seeing how the energy of that electron, which is in the nth orbital, is being affected by all the other nuclei. And this is going to give me some total value, some V naught, some constant value V naught. Okay. So if m equals n, I call this term, all of this V naught. Got it? So what is V naught? V naught is an electron is in the nth orbital. All the other nuclei besides the nth nucleus interact with that electron. That causes a shift in the energy of the electron. That shift in energy is called V naught. All right. So how does the electron in the nth orbital be affected by all the other nuclei? That's V naught. So it's not a hopping term, it's not a transfer term, it's like a cross term. Okay. Now, this scenario in which m equals n plus 1 or m equals n minus 1 will include terms in which the sum of all potential energies is causing the electron to hop from one atom to a neighboring atom. All the potential energies in the system, besides the nth nucleus, they will cause the electron to make a transition from the nth to a neighboring orbital. Okay, and we assume that transitions only to the nearest neighbor are possible, only to the immediate neighbor are possible. So let's call this entire term minus t, whether there's a hop to the left or it's a hop to the right. Let's call either of these terms minus t. So all the potential energies may cause the electron to transition from one orbital to a neighboring orbital, be it to the left or be it to the right. And we're not allowing two hops, we're just allowing a single hop. Okay, so and otherwise all other terms in which m and n are separated by 2 units or more, no such hops are possible. Okay, and no matter how many nuclei do they have, their interactions do not cause any possibility of hops beyond the first neighbor, beyond the immediate neighbor. So second nearest neighbor, third nearest neighbor hops are not allowed. So this term is 0. So if I would like to summarize all of this, this has 3 possibilities. Either it's V naught when m equals n, or minus t when m is different from n by 1 unit and 0 otherwise. Now this allows me to, so if you look at different kinds of tight binding problems, you'll have to find out this matrix element. Now in our supposition, we have provided the reader or the researcher or the scientist or the physicist with the premise that only nearest neighbor hops are possible. Okay, and the interaction of an electron with all the nuclei leads to just to some kind of energy shift upwards or downwards, and that is called V naught. All right, so that V naught is going to add on top of the atomic energy. So our HMN overall becomes delta Mn epsilon atom So now we have the following scenario. We have delta Mn V naught minus T delta Mn plus 1 or delta Mn minus 1. So what we could do is we combine the E atom with V naught N minus T delta Mn plus 1 plus delta Mn minus 1. All right, so far so good. By the way, this atomic energy represents the kinetic energy and the interaction of the electron bound to its own nucleus. Okay, and this V naught is the interaction of the electron with all other nuclei. But neither of these terms represents a hopping or a transition. The transition or the hopping is represented by this term in the Hamiltonian. Okay, so now if I were to look at the Schrodinger equation, which is summing this over all Cn's, giving rise to epsilon Cm, I would have the following. Now what I need to do is I need to solve this. I found out what the matrix element is going to be. So I can write this as plus V naught minus T m plus n plus 1 plus delta m n minus 1. All of this be multiplied with Cn, and at the end I would get epsilon Cm. All right. So now what this means, if I look at the left hand side, I'm summing over all n's, but I'm only picking up one value of n, which is equal to m because of the Kronecker delta. So the summation on the left hand side just withers away, and I'm left off with epsilon atom plus V naught Cm minus T delta n plus 1 plus delta m n minus 1. Cm is epsilon Cm. So far so good. Now I need to solve this equation, which luckily is an algebraic equation, and that will give me the C's, which are all that I need in order to construct the eigen functions. Now I assume an ansatz. I have a periodic function, so I'm always used to dealing with functions of the block kind. So let's use an ansatz in which my Cm is of this form, e minus I k m a over root n. This is for normalization. All right. So since this under root n is on both sides of this equation, so it doesn't really matter. So now what I would like to do is the following. I will just try to insert this in this ansatz and try to find out this epsilon. So E atom. So let me call this E naught just for simplicity. So this is my epsilon naught, E minus I k m a minus T by the way, since my m, so I really need to put in a summation over n here because I haven't yet gotten rid of this. So this becomes sum of n delta m n plus 1 plus delta m n minus 1 Cm equals epsilon E minus I k m a. What I could do, I could just focus my attention on this term, and I could write epsilon naught E minus I k m a minus T. Now m, I am summing over all n's. So by the way, this is a Cn. Sorry, this is a Cn. So this is a Cn here, okay? I haven't yet gotten rid of the Kronecker delta. So this is a Cn. So I'm summing up over all Cn's, and n has to be equal to either m minus 1 or n has to be equal to m plus 1. So this means that I can have C m minus 1 or C m plus 1. Epsilon E minus I k m a. But I need to put this in here, in here, and in here. Okay, and if I were to do that, I will get my desired result. Epsilon naught, sorry, I'm being a bit tongue twisting here. So epsilon naught E minus I k m a minus E minus I k m minus 1 a plus E minus I k m plus 1 a equals minus I k m a. So I can simply cancel out this term from both sides, this thing, and I'll be left with epsilon naught minus T E minus E plus IKA plus E minus IKA equals the energy. Lo and behold, I've gotten the energy. My energy, these are the Eigen energies of this tight binding Hamiltonian, are simply epsilon naught, which include the atomic energy plus that correction in the potential energy because of the presence of this large number of nuclei, minus 2t cosine of k. So this is the dispersion relationship for the tight binding chain. And I can plot this as well. If I were to plot this, this is what the dispersion relationship is going to look like. I have k on this axis. It's a one-dimensional problem. I put in my Brillouin zone boundaries pi by a and minus pi by a and simply plot. It's a cosine function. So the plot is, it's inverted. It goes down by minus 2t units and it's along a baseline of epsilon naught. Suppose my epsilon naught, without loss of generality, I call it to be 0 because this is just a constant. So this is what my dispersion relationship is going to look like. Okay. This point is minus 2t. This point is plus 2t. This is a particular band. Electrons fall into this band depending upon how many electrons exist. If there are n unit cells, one atom per unit cell, n atoms, one orbital per atom, one and total, it's just one electron that has to fill into this entire chain. Then, and one atom provides one electron. So there are n electrons. There are going to be 2 pi over L spaces in between. Okay. And the separation between 2 points is going to be 2 pi L, and there are going to be n spaces in between. And since these electrons can pair up in spins, half of this, if we just have one atom, each atom contributing one electron that is going into its orbital, half of this will be occupied. And we'll have a metal because the other half of this band is unoccupied. If each atom, still one orbital, contributes 2 electrons, then the entire regimen, the entire band will be occupied and we'll have an insulator. But how can we get multiple bands in this fashion? By the way, the bandwidth is 40. This is the width of the band. If the parameter T is large, which means that the atoms are closer together, then this bandwidth is going to reduce. Okay. And how do we get multiple bands, by the way? We can get multiple bands if we start off with, for example, 2 orbitals on each atom. Okay, if we have 2 orbitals on each atom, we could get multiple bands. So let me draw this scenario in front of you. So if we have one band, one orbital per atom, then these atomic orbitals, they are going to fan out into a sequence of bands, into a sequence of energy levels. So I'm just exaggerating the separation between these energy levels, but this is a fanning out of energy levels and they form a band. And this width here is 40. Okay, this is the bandwidth, the width of this band, which is called the bandwidth. So really, this band forms almost a continuous region in which energy levels exist. The spacing between these energy levels that make up the band are really small because the k values are really small. Each k value is separated by 2 pi over L because of the finite size of this chain. There is quantization of the k values, and all of these k values give rise to tiny, tiny steps in energy. But they're so close together because the number of atoms inside a macroscopic solid is so large. There are so many unit cells that these energy levels are spaced really finely together and they form almost a continuous band. This is called the first band. So if we had, so let me redraw this band here. So here is my band. If there are, so this is the case when we have one atom per unit cell, one orbital per atom, and one electron contributed by each atom. So the single electron goes into the single orbital. So in this case, what's going to happen? Half of this band is going to be filled. By the way, what is this axis here? This axis here represents A, or the distance between two atoms in the chain. If the atoms are brought closer and closer together, the T goes up, the bandwidth goes up, the hopping integral, also called the exchange integral, goes up, and the bands spread out. If you started off with two orbitals, then if the second orbital, so beyond this point, remember that the electron orbitals are not fanning out into bands because these are isolated atoms. So one orbital can have a higher energy than the other orbital. Suppose this is the 1s and this is the 2s band. The 2s orbital has a higher energy than the 1s band, and they're far apart. So if we tight binding will also occur for the 2s band with the higher orbital. So this will also fan out. At a certain region, the bands can overlap. So this is where the bands start to overlap. All right. So the bands can also overlap. And this is very similar to the situation that we discussed in the previous lecture when we were discussing Fermi surfaces. If we have a Fermi energy or a chemical potential that lies here, then this band will be filled and this band will be filled. And you can still have a metal. So if I have this scenario in which there exist two orbitals per atom, and I have two electrons donated by each atom, then naively the lower band will fill up. Okay, all of this will fill up. However, if the atoms are close together, which means the bands start to overlap, then the first band will also remain empty to some extent, and the second band will also remain empty to some extent. The second band will take up some of the electrons. So both of these bands will now be partially filled. Let me redraw this because there's a mishmash of colors over here. Let me redraw this. Excuse me. The first band, second band. I have two orbitals per atom and two electrons per atom. Okay, and this is my spacing between the atoms. And now what I get is if I have two electrons per atom, then suppose my spacing is somewhat here, then this band will be completely filled. All right. So this material will behave as an insulator because the Fermi surface is at the edge of the band, and then there's the band gap between the next band. If the atoms get closer at this range, still I have an insulator. But at this point, what's going to happen is I'm going to make a transition from an insulator to a metal. And if I go further close in terms of the spacing between the atoms, then both of these levels are going to be occupied. both of these bands will be occupied. All right. So the top band is partially filled and the bottom band is partially filled. And we have an insulator to a metal transition at this stage. So even with divalent atoms, if you have more than two orbitals and they start forming overlapping bands, you can still have a metal in one dimensions as well. So this is the tight binding model that I wanted to discuss. The tight binding model also gives rise to bands, and there are energy gaps at the band edges. Now, what we're going to do in the next lecture is we're going to look at some more examples of tight binding Hamiltonians. Suppose instead of having, let's do this quantitatively in a correct fashion. How do these bands overlap if you have two orbitals per atom? How do we get a two band structure in which there is a gap between the lower band and the upper band? If we have uh, a lattice that is square and it's two dimensional, what kind of dispersion relationship do we get then? Then our K space is also going to be two dimensional. If we have a hexagonal lattice as we have in graphene, what kind of structure do we get in that case? So this is where I would like to finish off today's lecture. I hope it was useful, and now I hope to see you on Thursday, inshallah.